here. So what is the one of them? The simplest one is this one, the Frobenius norm one. So this is the ON invariant or orthogonal invariant distance in the bundle space. And now again you can define the alignment distance by aligning, but now instead of GLN, you see that here is ON. So this will be again a distance. And interestingly, this notion of standardization also has been used in Kendall's shape analysis theory when the same standardization happens, so that you go from the group of similarities to the group of rotations. So let us take an example. The example that we start with, suppose that we have this system of, where for the video application, the rank of C is a tall full rank matrix. Then the one standardization is that you just apply the through the SVD of F, C, you can go to this space where the C transpose C is equal to identity. You can do this because it's full rank. Then here you will define the distance as the alignment distance as one aligning to realization through this Frobenius-based distance minimization. So, and also we have developed a fast algorithm for this. In general, if you have other LDS spaces, you can do this through something which in control theory is known as balancing. I will not go through that, but it's always possible to do this reduction, and it's always possible to get this ON invariant distance and use it to define a distance in the space of linear dynamical systems. So let us look back and see what we have been doing. So our target space was the space of the dynamical systems of fixed order and fixed type, and this alignment distance that I defined in general is not an intrinsic distance, so it's still an extrinsic distance. So, but it's not coming from an infinite dimensional ambient space. The picture looks like this. So if I have two systems, M1 and M2, if I use the infinite dimensional ambient space, I will get this shortest path. Ideally, I want to get this one, which is the intrinsic geodesic based distance, but that's difficult computationally. Instead, I will go to the ambient space, which is not very large. Okay. Another criticism of this distance might be that this minimization is difficult in the sense that it's not convex. You will get local minimizer, but that's also the same thing that if you use with if you want to do Riemannian distances. When the geodesic, when you find a geodesic, at least you're finding a local minimizer to the length function. So this global non-globalness is something that we have to deal with in nonlinear spaces usually. And one advantage of this is that instead of solving large sets of ordinary differential equations which come from geodesic equations, you just solve a static optimization. And this idea can be extended in various ways. For example, you can replace B theta. You can get rid of this OM group in the input side by replacing B by B1, B by BB transpose. Or you can use other norms than the Frobenius norm here. For example, also you can use the norms from the Stiefel manifold in the C part. You can do a bunch of other things. You can do, for example, try to define distances which are invariant, insensitive to scaling. For example, you can force the norm of B and C to be equal and then define the distance there. Again, you will go to a submanifold of realizations in the top space and then try to align the realizations. I briefly go through this averaging algorithm. So we want to minimize this Fresnel sum of the square of distances, and then is the alignment distance. So if you go back to the definitions, you will see that this minimization is really two minimization. One is over a realization for the average, target average, and also the other one is alignment, and the alignment problem that I talked about. So at the end of the day, what happens is that you will have a coordinate descent algorithm which is alternating between alignment and finding averages. So what happens is that you will choose your realization, you will align it to a target average. After you do alignment, you do, because of this Frobenius norm, this decouples and to Euclidean averages. So you align realization with respect to a target realization, and then you average Euclidean average, and then at the end you should do a orthonormalization on C. This comes from the condition that C transpose C is equal to identity, and you iterate. So this is a thing that you can have. It happens also in other, for example, shape space averaging algorithms. You could have such a thing. And here is an example that we worked out. So the situation is that we have 55 videos. We know that they come from 4 different classes, but we don't know the classes. So we will run a k-means algorithm. If you recall, k-means algorithm is based on finding the centers for clusters and then comparing the centers and keeping iterating till you get clear clusters. But you need to be able to find the centers. And here, the algorithm uses this align and average algorithm to find the centers, and it converges to these 4 classes, which are running to the right, running to the right and left, and walking to the left. And these triangles are the average or the center of the clusters. Okay, so the conclusion is that the linear dynamical systems can be used for classification and clustering of high-dimensional time series data. We introduced an alignment distance based on the idea of aligning realizations of the linear dynamical systems, and this is an extrinsic distance in general, but the ambient space is a small distance, a small space, and there are lots of things to